Hey, welcome back to another presentation in your weather and climate course. This time we'll be discussing precipitation and the different types that we observe on the Earth's surface that comes from our atmosphere. We'll also be able to discuss the shape of water droplets, the size, and again, the different types of precipitation is the big part of this. We'll also wrap up this presentation discussing drought conditions, and also looking at just overall precipitation values and annual averages across not just the United States, but more specifically in California. That being said, let's get going. So let's begin talking about some of the basics of precipitation. Now, as we can see, there are several forces that act upon the water droplet to ice crystal process, which is found inside of clouds. We'll be looking at the wind. Another cause would be the atmospheric stability. We'll look at gravity as well as the drag or the friction itself. Now, when a droplet reaches a certain critical mass or size, the force of gravity will exceed the other forces and essentially the precipitation will fall. Now, to put it in perspective though, rain droplets are about 100% times larger than the very, very small droplets that are found inside clouds. So it's just kind of interesting to put that in perspective, that when we see these beautiful clouds that are floating by, depending on which type, generally nimbus or rain-bearing clouds, but even at that point, those clouds that are floating by that do have water droplets within them, they're very, very, very small, and that's why they're able to, essentially be suspended. As we learned in clouds, and understanding the different types of clouds, that essentially clouds are constantly falling. There's gravity involved. The cloud is slowly moving, being moved by air and being pushed down. Of course, through convection cells and the types of heat that's rising, it can push the cloud back up a little bit and rejuvenate it. But essentially, clouds are constantly falling. But you need enough droplets for that, that sheer size for it to become so heavy that it will then be able to free fall, which is, that's kind of an interesting point to make. Now, moving forward, the formation of precipitation can be broken into three groups. We have condensation and deposition. We also have collision and coalescence, and we also have the Bergeron process. So condensation and deposition involves warm air. Collision and coalescence means it involves warm air as well, but the Bergeron process includes cold air. So let's talk a little bit more in depth on some of these topics. Now, condensation and deposition can be observed just like this diagram on the side. In fact, I'm drinking a little drink here. It's my little energy mineral thing, and you can see there's water droplets on the outside. And often we think, oh my gosh, my cup is leaking, but it's not. It's actually what's happening in this case is that the contents inside the container with the ice and the drink are cooler than the surrounding air on the outside of this container. And in doing so, it's actually pulling the moisture, the humidity that's in the air, and allowing it to grasp on to that temperature difference and essentially condense and turn into larger droplets that can be observed, and then at some point enough of them will merge together until they become too heavy to be stuck on the side of the container and will drop down. So it says here, as long as the rate of condensation exceeds the rate of evaporation, water will be deposited and accumulated on condensation nuclei. The droplets will grow very slowly and will rarely produce raindrops. So even though we do see these droplets on the outside of my container and in the image that I'm sharing with you, those are very, very small compared to raindrops that we'll be seeing that come out of clouds. But still, it is a process that we can observe. Now, collision and coalescence is actually, I think that's probably one of my most favorite out of all of it. Now, as water droplets are falling through the air, so they finally become heavy enough that they can break free and they start to fall. And as they're falling through the cloud and through the air, those droplets will, larger droplets fall faster than smaller ones themselves. But what will end up happening is that larger drop will start colliding and touching other droplets and merging together and growing bigger and bigger. Think about when I think about this, I think about the car wash, or it's a rainy day and you're sitting in the car looking at the windshield and you're watching that droplet on the top of the glass, and it slowly is dripping down, and then it bumps into another one and gets a little bigger, and moves faster, and until it finally goes all the way to the bottom. And that's the same process of collision and coalescence. Now, if the droplets coalesce, a larger drop will be formed. If the droplet gets large enough, it will obviously fall and turn into a free-falling rain droplet. But this is a way in which very, very small nuclei of water will merge with others to become droplets of larger substance, to the point that they'll become too heavy to be suspended within the cloud and will free fall themselves. Now, that paints this new picture here. We have lived our whole lives thinking that water and rain droplets look like this, and I'm sorry to tell you that they do not look like that. I know, this is like one of those moments, the mind is blown. What's interesting about rain droplets is that, as we learned in other presentations, it starts off as a completely spheroidal round droplet. Now, once they become, in the ability of falling, what ends up happening is, as you can see in letter C, that the pressure, the air pressure, and the density of the air is pushing up. The force is pushing up against that droplet as the droplet's falling down, and what it does is it creates a flat bottom. And at some point, if the droplet is large enough, the air will create this concaved type of feature. And if the water droplet's large enough, and the air is dense enough, and so on and so forth, it will actually cause that droplet to split, and you will then create smaller droplets. So that's kind of an interesting piece when you think about just rain, when you've experienced any type of precipitation, but specifically rain, that sometimes I was in Florida recently, and I felt like the raindrops were the size of quarters. They were falling very hard, very fast, very large. But what's interesting is I've also experienced rain that was very heavy, but they were very small droplets. So we can see that there's a difference in the droplet size, and a lot of it has to do with this diagram that we observe here. So as we can see, we're looking at the way to read this is that this is a no-no, letter A. Moving into letter B, we can see that they're less than 2 millimeters, and they're greater than 2 millimeters, less than 5, and then greater than 5. And essentially this process of, as that droplet falls, it has the ability to split apart and become into 2 and more and more. Now, obviously, within the falling process and in the cycle, there is the addition to the coalescence or collision of droplets to make them large again. They can split again, but it's very interesting. Things that we can also take into consideration is the atmospheric temperature, because it can start as a rain droplet, and if the air is still very cold that it's going through, it can freeze and turn into hail, or it can then melt again, depending on if there's a warmer layer, depending on the time of day and what type of season we're experiencing. So it's not uncommon for droplets to be a droplet, freeze, melt, and then in that process get larger and larger. And then obviously then we experience things such as hail that are like solid pieces of ice, because it's gone through that priming of warming and freezing, which is kind of interesting if you think about rain droplets. Who would have thought that there'd been so much information on precipitation? So then we can move into what's called the collision efficiency. So this kind of brings in, into full circle, no pun intended, towards these droplets. But a droplet itself must be larger than the other droplets in order for an efficient collider to be in existence. If the drop is too big, it will be less efficient because it creates high pressure that can actually end up pushing the droplets away. So it's very interesting that there is physics involved in this, and depending on the size of the droplet, if there's a sweet spot in which it can able to grow by bumping into other droplets and becoming larger, but at some point it could become too large that it's such a heavy mass that as it's falling, it actually causes the air to push away. So there is there's math involved in this, but we're not interested in this purpose. It's just more of taking into consideration the process in which water droplets move, that it's much more complicated than just rain. That there are different efficiencies that are needed, there's different processes that are involved, and there's different shapes that can be observed. And so the last one that I wanted to mention for this part of the presentation is the Bergeron process. So vapor pressure over ice is less than over water of the same temperature. Thus, water molecules move from water to ice and then freeze. So if the crystals get large enough, they will fall. And if they fall through cold air, it would be snow. If they fall through warm air, melting occurs. So I kind of mentioned this already, just like 3 slides ago, when looking at these different processes. But you have this ability of water falling, and if it goes through cold air, it'll freeze. If it goes through warm air, it will continue to melt and stay as a liquid state. But it is possible that it can go through cold cold, warm. You could do it depending on the atmospheric condition. But this is the Bergeron process, which I think is another interesting attribute to precipitation. So something else that we can talk about now that we've introduced the idea of just snow is that we can look at the growth of ice crystals. And I think that as a kid we were all super interested in snow because we knew that, okay, it's like a fingerprint. No two are going to be the same. They're geometric in design. They're very unique. We all did that little paper craft where you cut them apart and everyone's snowflake was a little bit different. And I think that's a really exciting part of precipitation because we often don't think of snow as being precipitation, and as we'll talk about in a couple slides, there's lots of other types of precipitation other than just rain. But we have two processes that we can observe through the growth of ice crystals. There's riming and aggregation. Riming is super cooled, water freezes into an ice crystal, done deal. Aggregation is ice crystals will join together to form larger snowflakes. So riming is like the growing of the initial, and then aggregation, like the word aggregate, I don't know why it's not important, but I'll just share it anyway. When I think of the word aggregate, I always think of Abraham Lincoln because there was a speech that he gave where he talked about the aggregate of his education, meaning that the combination and accumulation of all of his education amounted to X amount of years. So that's kind of what's happening here. Is an aggregate means that, okay, well, we are now collecting all the ones that are around and they're able to merge together to make something a little bit bigger and more complex. So this diagram here, I just thought this was interesting to share. Again, I'm not going to expect you, in my class at least, to memorize all this, but to see that there are efficiencies that are needed when looking at either the saturation amount, grams per cubic meter, and also with decreasing temperatures. So the cooler it gets, we get, depending on the amount of moisture in the air, the humidity, and depending on the temperature, will create different types of snowflakes. So we get to really observe these differences, which, if you were someone who was studying just, snowflakes, which doesn't sound like that would be a job, but it is, you would be able to look at a particular snowflake and see that these, platy sheets, depending on their size, we can also distinguish what type of temperature would have been needed in order for that to be created, to be observed. So let's wrap up this presentation looking at the different types of precipitation. So these are the top 6 that are responsible that we can observe for precipitation values that are measured throughout the world. There can be a mixture of them in any particular storm, but these are the 6 that we are going to be studying in specific for this presentation. Rain, snow, graupel, sleet, freeze rain, and hail. So as we can see, each one of these has a very definite and defined definition. Rain or liquid drops or ice. Melting occurs as it falls through the warm air. Snow is when we have ice crystals that grow within the cloud in a variety of shape based on the temperature, as we've learned already. Graupel is an interesting one. When I think of graupel, it says grow by riming, contains air pockets, and has a spongy texture. Graupel is that, for me, that perfect ice, like the little round pellets, and they're kind of crunchy, they're not solid, they're kind of fluffy. That's graupel, which can often be confused for hail. Hail's a lot more dense. This is very fluffy, almost spongy in a sense. Then we have sleet, which is ice crystals melt as they fall through the warm air. The water droplets then freeze again due to the cold air below and turn into pellets and sheets in a sense. Freeze rain are ice crystals that fall through warm air, then begin to melt. Then the liquid falls through air at 0 degrees Fahrenheit or Celsius and freezes and freezes upon impact of the surface. So freeze rain is essentially that water droplet that will fall, and then when it hits the windshield of your car or the surface, it immediately freezes into a piece of ice. Theoretically, it's also that you probably have seen those things on TikTok and on Instagram where it's like the water bottle and they put it in a freezer for 30 something minutes, and then you bring it out and then you impact it, and that impaction will cause the ice to freeze within the water bottle. It's kind of the same idea. And the last one is hail. So strong updrafts in a cloud force ice upwards, causing it to continue to refreeze and then develop layers and really priming that block of ice that will end up falling at some point. And it looks like a small a cobble to a boulder. Texas in particular gets hailstorms that make all their cars look like golf balls because they're about golf ball size, but it impacts the cars in complete patterns that it makes them all rippled. Very dangerous. Hail can be incredibly dangerous and very large depending on the environment involved. So then we can move into just visualization of these 6 types of precipitation. So sleet, snow, freeze, rain, hail, graupel, and hail. Maybe you've experienced some of or all of these. Be sure to comment below. But I just wanted to include images to kind of share the different types of precipitation. And again, it's interesting to think that this is precipitation. We are constantly on climate watch and with drought watch because, yes, rain is fantastic because it fills our reservoirs, but we really want these other types of precipitation up in the high elevations and high altitude where it gets stored as ice and snow packs that slowly melt during the summer seasons, which will help replenish our reservoirs and rivers during a time of the year in which we don't often receive precipitation. So as the climate continues to change, we are observing not just warmer weathers, which means the ice is melting faster and we're not having those reservoirs or the storage as long within the summer as we used to. We're also seeing a decrease in overall precipitation of all types. So we're not accumulating enough to begin with during our winter months to withstand the melt. And a great example, just if you want to take the science out of it, a great example of seeing how climate is changing and that we are receiving less precipitation in shorter periods. Think about just going snowboarding, right? If you ever go skiing or snowboarding, whether it be in Mountain High or if they go to Mammoth or Big Bear, you have observed in the last decade that the snowboard and skiing season is continuing to get smaller and smaller if there's even one to begin with. And we're not experiencing these long periods in which snow is available. In fact, some of these places have to manufacture snow to just really extend their season a little bit longer by grinding up ice. So these are things that you definitely have experienced, especially within the last couple of years. Which brings us to this map here. Again, to just kind of put things in perspective, this is a map of mostly North America, but specifically the United States, looking at the average annual precipitation. So we can see which areas receive the most versus the least. So, it's based on color. So the more green to blue purple, the more precipitation that's observed. Greens are looking at perhaps 40 to 50 inches of rain per year. And then areas that are more on the lighter green to yellow to red are we're looking at 20 inches and lower. So looking at areas, here's my mouse, areas like in Los Angeles, Death Valley, places like that. Moving on to the Great Mojave, Mojave Desert receives maybe 2 inches of rain per year. Los Angeles gets, and especially in the surrounding areas, maybe 12 to 14 inches of rain per year, but we receive very little precipitation compared to the amount of people that consume the water itself. And then we can see, areas within the South and East Coast, they get traditionally a lot more precipitation, but especially in the northern areas, they're not only getting a lot of precipitation as rain, but they also get it as in snow. The Sierra Nevada do get some precipitation and some snow as well. That's part of the rain shadow effect, while you have more moisture available on the western side and it's much drier on the eastern side. But that's for another presentation for another day. But this is just kind of putting it into perspective, especially someone who lives in California, where we're used to 14 to 12 to 14 inches of rain per year, maybe a little bit more during an El Nino year. But it's just weird to think that there are places, in Northern California and on the East Coast, that it's not uncommon for them to have, 80 or 100 or even 120 inches of rain per year. And that's almost mind-boggling. But then again, the rainforest, and the Amazon, it's not uncommon for them to get over 200 inches of rain per year. I mean, that's incredible to think about how much water that is. They just get it all at once, and it can't be stored, and it gets washed into the ocean, so it's considered a loss. So let's look at California. This is a diagram from April 13th, 2021. You can certainly go through the droughtmonitor.unl.edu. You can access the most recent for your area, specifically in California. But I just think this is really an interesting piece of our culture. In California is our weather and climate. Remember, weather's the day-to-day stuff, but climate is long-term. So when we start seeing, 1 year's worth of data, what's happening, and we can see what areas are experiencing already in April, in the middle of spring, exceptional drought, extreme drought, severe drought, moderate and abnormal drought, and then just a very few sprinkling of areas that are not experiencing drought at all in the northwestern state corner itself. But again, looking at areas of Los Angeles, we're already looking at moderate to severe drought already in April. And places beyond the San Andreas Fault, which is kind of ironic that it runs that way, everything beyond the foothills and the San Gabriels are already in extreme drought, and if not exceptional drought. So it's just something that we really look at. We weather stations all over, looking at the different types of precipitation that occur, and how can we utilize that water as a form of sustainable life, whether it be flushing toilets, for agriculture, for just drinking and to consume. So I hope that this kind of paints a picture of the different types of precipitation that we look at. We can also look at the greater data of storage and how much we receive in areas that are experiencing extreme drought due to climate change. Again, the big thing is that we learned that water droplets are not that traditional teardrop shape, that they are a little more complicated than that, and we explained why. I hope this was helpful. Be sure to ask questions below if you have any. Maybe you remember or you experienced some of these types of precipitation at some point. Be sure to add that below. Don't forget to like, subscribe if you have not already, and we will talk soon.